Warning, this video contains a lot of heavy code which some viewers may find disturbing. I have been using the MRF24L01 and I had to learn about these off howtomechatronics.com. Honestly, this is a great tutorial, so if you're going to get into these devices yourself, please give this a read through. But I'm going to skip ahead to where the code examples, because we all love a bit of copy and paste. So these are the two sketches we get, one for transmit and one for the receive. I have two Arduinos plugged in, which I'm going to upload to. So they have just finished uploading, and if we open the serial monitor for the receiving Arduino, we get this text. So this Arduino is sending one way to this Arduino. But for our case, we don't want two different sketches. We are going to use one Arduino with one generic script for both transmit and receive. So we're going to try and combine these sketches into one. I'm going to create two functions, one for handling the sending and one for handling the receiving. So in the send sketch, I'm going to move the code out of the for loop and move it into the send data function. I'm also going to move the stop listening and the open writing pipe into send data. And for the receive data function, I'm going to move everything from this for loop, put it in here. I'm also going to take the start listening and open reading pipe. I'm also going to take the serial begin and put it in the setup function of our send script. Now, this is the most important part. Because we have two different modules, we are going to have to store two different addresses. This one is going to be the send address, and this will be the receive address, which I will give a value of 2. Next, we'll have to update the sketch references for these two addresses. So these functions are done, however they're not yet being called, so we will call send data and receive data in our loop. However, we have to send data only when the other Arduino is expecting to receive data, otherwise it will be like two people shouting at each other and no one is listening. Just a lot of noise, literally a lot of electronic noise in the air. So to do this, we will call send data at intervals of time and have the Arduino be listening in all other cases. We will need to create two variables. Last send time will hold a reference of when we last sent data, and send delay time will be the interval time before we send again. In the loop function, we set up a common time-gated pattern where we check if it's time to send, and then we refresh when the last time we did send. So I believe this is working code. How it works is we first enter our for loop, we check if it's time to send, it is, then we go into the send data function where it opens a writing pipe of the send address 1, and then it sends, well, we can actually tell it to send anything, so we can change this to our receive address. I will also take out this delay here, well, reduce it to 1 millisecond. After this, we will finally go into the receive data, where it will open the reading pipe and the receiving address 2. And if we have something to receive, we will write it to the serial monitor. So I'm going to upload this sketch to one of our Arduinos. And before I upload to the second Arduino, we have to make sure that these addresses are swapped, so that one Arduino's send address is the other Arduino's receive address. I hope that makes sense. So on COM9, we are receiving 0002. And to check COM8, I have to use PuTTY, as Arduino IDE only allows monitoring of one COM port. There we go, 0001. So they are actually communicating with each other now. Lovely. It's what you like to see. And we are just sending one script now, so we don't need to use the receive script anymore. Ta-da. But it's going to be very tedious to keep changing these values around. And if we introduce more Arduinos, it's just going to be more work. So we're going to change the way we address the addressees. My best guess, we'll use an array. Oh look, an array. These will be the addresses of up to 6 Arduinos. We also have to cache the value for how many items are in this array. And this variable we will update prior to sending to an Arduino to tell it which address it is. This will be an array index number. If we choose 0, it will be the first address in the array. If we put 1, it'll be the second, and so on. With this, we have to change the address references. For send data, we will loop through all the addresses in this array. Our send data now looks like this. A simple for loop with the I variable addressing all of the addresses. And we also need to update the address of our current Arduino using this ID. This is its receiving address. But there is an issue now where we can send this information to ourselves, which we don't want. So we will use an if statement to ignore this ID. We don't use break because that would end the loop. In receive data, we will now have a reference to the address of this Arduino using this ID, which in this case will be 0, so our receiving address will be 1. Let's upload this code just to check that it still works. Making sure to change this ID for each Arduino. And as we expect, data. This is great and all, but we won't actually be using the serial monitor for our final build. So I have wired up an LED on each Arduino so that it will light up whenever we receive data, or that another Arduino is within close proximity, mimicking the perk. We will create a variable for the pin number of the LED, and then set it as an output in setup. Next, we add a variable to keep count of the amount of Arduinos in proximity. I will call them rats from now on. Next, we'll add a function to handle all our buff stuff, which for now is just going to compare rat count. If it is greater than 0, then we will light the LED, otherwise we will turn it off. Next task is to decide when to call this function. We could call it in every loop, but it would be inefficient. We know send data is called every few seconds, so we can put it here and update periodically, so we call our buff. But we still need to assign a value to rat count, and since if we have received data, this would mean a rat is nearby. So in receive data, we will increment our count, making sure it's inside the if statement. Also, for now, we'll add a printout of the rat count for debugging. But since this would keep adding up, we will need to reset it back to 0 at some point. So I'm going to add this at the end of our buff function since it happens at intervals of time. So let's test this script, remembering to update this ID. Oh, and there we go. Since now that the LEDs have come on, we must have received some rats. And if we look in the console, we can see some rats. And if we power off one of the rats, then we can see there's no communication anymore. And if I turn this back on, you can see that the communication has been reconnected. But we set up this code so that we could work with multiple Arduinos, so I will get a third on the boil. Now, this monstrosity that you can see on screen was my first attempt of a mock-up for Rat King. I tried to use a string of LEDs to represent the in-game LEDs. That didn't really end up well. But I have uploaded the code to this third rat, so if I power it on, this LED light should illuminate, which it does. Great. And also if we go into our serial monitor, we should see more than one rat, which we do. Great. You will notice that these values are flickering from 1 to 2 rats, maybe even 3. This is because every time you see a rat, we are outputting to the serial at that instant, not at every interval. We want a value that is constant at the end of every send data interval, for reasons that will make sense shortly. So we will add this variable called buff count. And in the buff function, we will cache the total rat count into buff count. Now, it may not be obvious, but this third rat actually has a motor attached. This means we can start testing the fire rate mechanic of the perk. Ooh. We need 2 new variables, one for the trigger input pin and one for the MOSFET or switch output. Then we assign the I/O type of these pins in setup, and we create a new function called fire. This code will simply turn on the MOSFET which controls the motor for as long as the input motor is high. Nothing fancy just yet. Finally, we call the function in our main loop. I'm just going to make sure that the code still works, so bear with me. Remember, save often, check often. Okay, I'm going to attempt to pull the trigger on the airsoft gun. Okay, that works. Sorry, headphone users. That rate of fire is going to be our end goal, but now we need to limit it as per the perk of Rat King. So we will use the buff count to allow us to do that. Remember that this variable is the steady value of rat count. This value alone is not going to be able to do that, so we are going to need to have 3 more variables. We are going to use the same pattern that controls the send data rate time interval, but use it to control the mortar rate of fire. Last fired will hold the value of the last time we fired the gun. Fire delay will be the interval between shots. And MOSFET open time is the time it takes for the mortar to complete 1 full firing revolution. Lastly, we add this bool fired flag. This is used to keep the MOSFET open after we've initially fired. Now, our fire function is going to change a little bit, so allow me to explain. Firstly, we check to see if our trigger has been pulled and we have not yet already fired. Then we will set a flag to say that we have. We will then open the MOSFET switch and record the last time we fired. By doing this, we will cause the gun to fire endlessly, so we have to tell it when to stop. We will do this with a timer strategy and check for elapsed time. If the timer has run out, then we will set this MOSFET pin off. This will allow the gun to fire and stop firing after a brief moment. The final if statement will check for the fire rate. This again is using the timer strategy. If the fire rate delay time has elapsed, then we can fire again. Okay, so testing early and often, I'm now hoping to see that there is a rate of fire delay. As you can hear, we have a fire rate of about 1 a second. Although I say 1, it was more of a 3-round burst every second. But we can adjust this with the MOSFET open time delay. I will try 50 milliseconds. Okay, so I'm hoping now for just 1 rate of fire a second. Perfect, that sounds like what we need. But this is hard coded to fire 1 every second. So how do we change this depending on the amount of rats nearby? We will simply change this to an array, like we did with the addresses. Then, the buff count variable will be used to index of this array. When there are no rats, there will be a 1 second delay. When there is 1 rat, half a second, and so on until it gets to fully auto. Since I only have 3 rats currently, my array is going to look like this. We then need to change the reference in Fire to include this array index. I'm going to turn off all but 1 rats, so we can see the 0 perk. So there is no LEDs on, so we expect to see 1 fire a second. As you can hear, there is. So I will add 1 rat. Wait for the lights. There they go. So now I should expect to see 2 every second. Which you do, great. And then finally, if we add the last rat, we should expect this to see full auto. Amazing. So the only issue now is all this breadboard isn't going to fit inside here. So I have here a side piece for the Rat King. And this is where I was hoping that everything would fit inside. And it's not going to. So we're going to have to maybe design our own PCB to get all this to snug down in here. So that's the next job. And through the magic of editing, the job is done. The PCB is long and slender so that it will fit in the crevice. I have no footage of how I got to this point because, well, I outsourced it to a friend who actually knows what he's doing. But let's get started with disassembling the motor and wire everything together. Here I called for my friend for aid, and he answered. Watch him solder as I talk through the circuit. The circuit is very basic. 5 volts being supplied to the trigger contacts, and then a pull-down resistor to an input comes back from the trigger contact switch, an output to the LEDs, an output to the MOSFET to control the motor, and of course the signal cables to the NRF wireless transceiver module. The gun originally has the battery power soldered onto the trigger contact switch, so it was desoldered here so that the power goes straight to the motor. The original battery was a mini Dean's connector, but since I upgraded the battery, it needs to have a regular Dean's connector fitted. These twisted cables are for the trigger switch. The LEDs are cabled together with connectors to make removing the top slide easier. One thing I didn't talk about in the last video was just how much of a pain having all these random cables trying to fit into a small area. If I was to design this again, there would be so much I would change. But don't just copy this circuit. I don't have that much experience with the electronic circuits, so I've definitely overlooked something. Love you.